We now determine the length and width of this rectangle, which is bounded by x-axis, y-axis, and the graph of the line y equals 6 minus x by 2. We determine the dimensions of this rectangle so that its area is maximum. So first, let's write the area of this rectangle, and this is written as A equals length times width of the rectangle. The length is represented as x, and the width of this rectangle is represented by y. Now, since this rectangle touches this line, we can consider the y as from the equation of the line, that is y equals 6 minus x by 2. So, replacing y as 6 minus x by 2, we get the area of the rectangle equals x times of 6 minus x by 2, and this can be written in function notation, that is a of x, which represent the area of the rectangle. This equals half of, we distribute this x, so it becomes 6x minus x squared. Now basically we have to determine the maximum value of this area function, that is at what x this area is maximum. So we are going to use the calculus method to find the critical point and also determine at what point of x the area is maximum. So first, let's find the derivative of this area function. That is, we find a prime of x by differentiating both sides with respect to x, and so this equals half of, we find the derivative of 6x, which is 6, minus the derivative of x squared using power rule is 2x. Now, to find the critical point of the area function, we set up a prime of x equals 0 and solve for x. And so when we do that, we set this up a prime of x equals 0, and this equals half of 6 minus 2x. Let's solve for x from this equation. So we can write 6 minus 2x equals 0. Otherwise, 2x equals 6. And this gives x equal to 3. So we can now see that x equal to 3 is a critical point. But we have to verify if at this critical point the area is maximum. For that, we should consider the second derivative of the area function. So let's find the second derivative of area function. So we will have a double prime of x, and this equals, we find the derivative of this a prime of x. So we put this half, which is a multiplier, and then multiply with the derivative of 6 is 0, and then we have negative 2x. The derivative of negative 2x is negative 2, and so this gives half of negative 2, which equals negative 1, and this is always less than 0 irrespective of, if we plug it, if we plug the critical point x equal to 3 into this one, it's always going to be 0, less than 0, that is it's always going to be negative because it is independent of x. So you can clearly see that this critical point x equal point of maximum, because whenever the second derivative is less than 0, we see that that point or that critical point is a point of maximum. So we were able to verify that x equal to 3, the area is maximum, and this means we can determine the corresponding length and width of the rectangle. So x represents the length of the rectangle, so therefore we see that length of the rectangle is 3, and then the width is given by the equation, that is y equals 6 minus x divided by 2. So let's plug in x equal to 3 into this one, so which gives y equals 6 minus 3 divided by 2, and this equals 3 half, or otherwise this equals 1.5 in decimals. So therefore we see that the width of the rectangle equals 3 half, or 1.5 in decimals. So thus we have demonstrated, or we have identified the length and width of the rectangle where the area of the rectangle is maximum. The length is represented by x, So we can write this as x equals 3, and this one is y equals 3 by 2 or 1.5.